We'll wait for 5 minutes and then we will start the class. Let us wait for others to join. Hello. Good evening, everyone. Am I audible? Mhm. Fine. My name is Abhishek Munshi. I am a PMRF scholar at IIT Jodhpur. So today I'm going to teach you a little bit about the losses and the efficiency of transformers so that you can able to solve the questions related to assignment 3. I have shared the link of the drive and YouTube. So you can find the previous lectures over there. So this is the YouTube link and the PPT link where you can find the lecture notes. Okay. Fine. So today we'll discuss a little bit about the efficiency. So what is efficiency? Basically, you have to know these things that the basic formula of efficiency is that the output power respect to input power to 100. This is the percentage efficiency. So if in a system there is some kind of losses, we can write this as, so we'll get the output power and there should be some kind of losses because no machine in this world is ideal, right? So 100% efficient is not possible. So you can write it in this way or in this way, right? Fine. So in the last lecture, I discussed a little bit about the types of losses in the transformer. See, first, there are basically two types of losses in a transformer. One is core loss, another one is copper loss. Fine. So core loss can also be subdivided into two categories, which I discussed last week. That is hysteresis loss. Another one is eddy current loss. All of these are magnetic losses. Okay. The copper loss is basically due to the I square R, I square X, basically I square Z. These losses are called copper loss. So in case of a transformer, obviously, if we have a input power P in, will not get that power, will get the output power with some losses subtracted from it. So the losses are core loss and mainly copper loss. Other than this, there are some losses like friction and windage losses. This is due to the separation of the core, the wind flow. In case of the huge transformer where there are breathers and all things are there. Another loss is a stray losses. Mainly, we consider core loss and copper loss. Fine. So there are two tests of transformer. One is open circuit test. Another one is short circuit test. In some case, we call open circuit test as no load test and short circuit test as load test. Fine. So,
Hello,
yes,
sir. I have a question. Actually, short circuit test you written like a load test. Now, whether it is a load test or full load test.
See, it depends like whether you have a load that is full load
Mhm.
and maybe half load. Obviously, we use the load that will be a full load. We consider it as a full load, but in some
Okay.
cases, what happens that we are uh, using a load which is not the rated load of that transformer. We use a load which is lesser than the rated load. We consider it as a lesser load of that. Suppose we have our transformer has a rating of suppose 100 ampere it can take.
Mhm.
That is the load of the transformer, but we are running it in a 50 ampere. So we can call it that the transformer is running in a half load. Okay.
Yes, sir. Okay.
So
Fine,
based
sir.
on that, the efficiency will obviously change because
Because I
load
square
means,
losses will change, you know?
yeah. Basically, load is the current. Fine. So
Okay.
if a current is decreasing, then obviously there will be a huge difference in your core loss and copper losses, mainly in the copper losses. Fine.
Yeah. Okay, sir. Thank you.
So you can see that this is the equivalent diagram. We already discussed it in 2 weeks all time that this is R1, XL1, this is XL2, R2. This is referred to the primary side of a equivalent circuit diagram for transformer. This is the primary resistance, this is the primary reactance, and this is the secondary reactance referred to the primary side. This is the secondary resistance referred to the primary side. And this one is the core of the transformer, where this is the magnetizing reactance and this is the core resistance, or we can call it as a magnetizing resistance also. Fine. So if on the here I already noted down, but because when I was not there and you will see the PPT, you can able to read these things properly. Fine. So basically, in case of a transformer, the efficiency, if we calculate at full load or half load, we have to know the percentage of load. So we determine that in this formula for the efficiency formula, see that X is the percentage of load, whether it is half load, whether it is full load, quarter load. We have to change the value of X in that formula. Fine. And S is the voltage ampere VA rating, or in some book we can find that it will be KVA rating. Because mostly the transformer ratings are coming in KVA. Fine. So this is also the KVA rating. So the formula comes down in this way that X is cos theta. Why cos theta? Can anyone tell me? In the
A
last
power
class, I
factor.
yeah, obviously power factor, but why we are multiplying KVA with the cos theta? Because in the last lecture, I already discussed the power triangle, right? So basically, we have kilowatt and kVAR. We are getting kVA, right? Correct. So if we're
Yes.
multiplying this with the cos theta, then we will get the real losses, right? So one is VI cos theta, that is the real power, and VI sin theta, that is basically the imaginary power. You can say in some cases, tell it that the reactive power. Hmm. So X is cos theta and X is cos theta. As I said that this is the output power, this is the output power, plus the losses. Fine. Plus losses. So what are the main losses? One is core loss. So core loss is P of I. Another one is copper loss. But as I said that copper loss is basically the I square R loss, and if we have doesn't have the rated current, we are operating the transformer in lesser than the rated current, then obviously the I square R losses will change. So the factor X square comes here in case of the copper losses. Someone asked me before going into this that what will be whether it is a full load. So in case of efficiency calculation, I said that, but if our load is decreased, then obviously the current flowing through the resistance and reactance will obviously lessen. And for that reason, the copper loss will also change. Right? So finally, the formula, please note it down because when I give some problems, then you can also participate over there and answer it. So note it down in your copy that this is basically x kVA cos theta, x kVA of cos theta plus x square into copper loss plus the iron loss. Okay. So this is the copper loss, x square copper loss is the copper loss at any load x. If the transformer is operating at a full load, then x should be 1 and the copper loss should be complete PCUFL that is given over here. Fine. Is it clear? So basically, this is the formula for calculating the loss in a transformer, or basically this is the formula for the efficiency. Here we have to consider x, which is the load percentage. Right. If you have any doubt till now, please ask me any questions.
Sir, we are adding x in a numerator and we are multiplying with the numerator denominator. So is it not in balancing the equation?
No, see what happens. Basically, suppose we have rated current means rated load I. Then X should be 1. And if we have a half load, suppose I is half, fine.
Yes, sir.
On that case, what happens? In upper side, you see that this is VI. So it must be multiplied with some half. So X should be half over there. And in case of copper loss, that is I square of R. So this I should be half I by 2 square. So X means half square. If you multiply it with the pre-existing I square R loss, then you can obviously get this loss, right? Is it clear? Suppose we have PCU, that is what? I square R, suppose loss. Only resistance loss, suppose. But we are conducting it in I by 2. So it will be I square by 4 into R. So that is basically 1 by 4 into I square R. That is 1 by 4 of your copper loss. That is half square into copper loss. And this is what the x square is. Is it clear?
Yes, yes, got it.
Okay. So next, we see that if we consider that the maximum efficiency as uh, this is eta maximum. If we have the maximum efficiency, then the variable losses are identical to the constant losses. Fine. So basically, the copper loss, which is load independent, it is the variable loss. Copper loss is the variable loss. Why? Can anyone tell me? You can say, don't worry. Copper loss is the variable loss. Why it is a variable loss? Because we didn't know the what should be our load. So fine. So that's why depending upon the load, our copper loss will change. So that is why copper loss is the variable loss. But core loss is the fixed loss. So it tells that eta should be maximum when we have PCU, but the copper loss is equal to core loss. Fine. In this situation, at a maximum efficiency, you can say that the load percentage should be PC or Pi you can write, that is by Pc. So maximum efficiency will took place at this load. So you can be asked in the exam the questions like what will be the maximum efficiency your copper loss and this one is given. You can ask like this that what will be the load percentage when we have a maximum efficiency, the copper loss and core loss are given. Fine. So in that case, the maximum efficiency can be xs cos theta by xs cos theta plus we said that is both this one and this one are equal. So this one and this one equal. So we can write it like plus 2 of this. I denote it here in Pi. So you can also write Pi Pc and fine. Since we have the maximum efficiency at Pc equal to Pc, so we can write the maximum efficiency as this formula. Please kindly note it down in your topic. Okay. So this is the graph for the efficiency versus load current. As I said that mainly the current is a load and depending upon the current, the efficiency is changing. So you can see that this is the curve for the efficiency versus load current. So you can see that at unit power factor, fine, coefficient, at unity power factor coefficient, this one, we will achieve the maximum efficiency. Uh, fine. And here it is written that the maximum efficiency at equal loading is every time you'll see that the maximum load point will be the load current point should be same and it doesn't depend upon the power factor. Right. The value of the efficiency can be changed, but the load current, the loading should be equal. From the curve, it is clear, right? So see, this is the efficiency at 0.8, this is the efficiency at 0.6 power factor, but at every case, we see that the load current is same. Fine. So this statement said this. Okay. Mhm. Now, as I said that if you have a core loss, then this is our the formula already discussed earlier. So as I said that the efficiency is the P out by P in, and this is you can write as P out by P out plus losses. So efficiency can be for calculating the maximum efficiency. See here, it will be 1 minus losses by input because suppose you consider it as the efficiency. So if we have to calculate it in this way, then this is a fraction, so we can write like 1 by and break it like this in this way. So it will be efficiency equal to 1 minus losses by input. So if you have to calculate the maximum efficiency, you can see that when differentiating this term, and after differentiating, we're getting that 0 minus this one, this one. So basically, for getting the maximum value, we know that then this should be equal to greater than equal to 0. If you have the minimum value, in that case, that this differentiation should be greater than 0. On that case, if we put it like here at 0, then see that this one is equal to this one. That is basically the copper loss is equal to Pi, which I already demonstrated over there that in this case, the copper loss should be equal to this iron loss. Then why it is, where from it is coming, that is basically from the basic mathematics. We are doing a differentiation of the efficiency and after which we are getting this formula. Fine. So now we will move into some problems. So based on this formula, I will discuss some problem, and after which I will discuss a little bit about the short circuit and the open circuit test, which we are doing basically for copper loss and core loss calculation. And we will discuss a problem on that, and we will end our class. So I'm giving a problem relating to this efficiency, which is the formulas which I discussed. So try to solve it. There will be a set of three questions. So suppose we have a full load of 350 kVA. The transformer has an efficiency of 95%. If the maximum efficiency occurs at 75% of the full load at zero point 0.8 on all loads, we have to calculate the copper loss at full load. Right. So try to solve it. I'm giving 5 minutes, and with the help of the formulas, try to solve it. Can you able to solve the assignments of the last week with the help of the this class? Everyone able to solve the questions?
Yes, sir.
Mhm. Let me solve it. See here, the kVA rating of the transformer is given. We don't have the copper loss and iron loss, so we can go to that way. So we have kVA rating 358 kVA. So what will be the real power output then? So it is VI cos theta. So this will be 350 into 0.8. So this is the watt kilowatt, right? So what will be the loss then? If you have a 95% efficiency, percentage efficiency is 95%. Fine. So the loss will be loss at full load. And zero point 0.8 power factor is this output power into 95% of this. So this is the loss at full load and zero point 0.8 power factor. So this is basically the iron loss plus copper loss. This is basically the iron loss plus copper loss. Now, in the question, this said that you have to calculate the maximum efficiency occurs at 0.75. Fine. So let me add a slide. So, okay. So here it is given that the maximum efficiency occurs at 75% of full load. Fine. So therefore, at maximum efficiency, I said that the iron loss should be equal to the copper loss. So it is 75% of the full loss. So the iron loss will be equal to the x square over there into the rated copper loss. So let us consider this as equation 2 and this one as equation 1. Uh, mm, mm, Fine, we're not able to copy it, so I'm writing it here. So we have another one that is iron loss plus copper loss, that is equal to 350 into 0.8 into 100 by 95 minus 1. Right. So we can write that from 1 and 2, we can write that iron loss, and this one will cut out this copper loss, so it will be mm, This loss at 75% must be equal to the total loss over there. So here, if we solve it, uh, if you use calculator to solve it, then we'll get the copper loss rated. Mm. So it is around, so we calculated the copper loss at 9431.571. Okay. Now the next part is that we have to calculate the iron loss. We calculated the copper loss as 9431.571. What are the other data given? That 350 kVA at zero point 0.8 power factor. Maximum efficiency occurs at 75% of the load. So now calculate the iron loss. We have the copper loss. Now calculate the iron loss. This is very easy. As I said, that iron loss is, as I said, that iron loss. So use this formula. You can write this. Fine. So someone get the correct answer. That is, if you calculate it, then it will be 75 by 100 whole square into 9431.571. So if you calculate it, it will be around 53. How much is it? 5305.26 watts, right? So we have iron loss and copper loss. Now calculate the percentage efficiency at half load. That is x equal to half. So we have the formula x is cos theta, x is cos theta plus x square of PCU plus PL. We use this formula. PCU we calculated as 94, how much? 31.57, and iron loss or core loss, that is 5305.261. So put this formula and can able to solve this.
Sir, S is how much, sir?
This was given in the question as 350 kVA, right?
Okay, sir.
350 kVA. Yes. Miss Rajani, you raised your hand. If you have any doubt,
Sir, cos theta will be 0.8.
yeah.
Sir, it will be cos 0.8 or sir, cos 0 or only 0.8, sir.
See, power factor is the cos theta. So you have to put
Oh,
power factor as 0.8 is given power factor. So cos theta is 0.8, not theta. Yes, many of you have corrected the correct answer. So if we solve it, that is half load, that is 0.5 350 kVA cos theta. If we solve it, that is around 94.81%. Right? Okay. Next question. We have a common data that the test result for a 500 kVA, 33,000 or 22,000 volt transformer. The open circuit test was conducted at low voltage side when high voltage side is open, and the short circuit test performed at high voltage side when low voltage side is shorted. So these are the test results. So see one thing for open circuit test, and it conduct short circuit test. So the loss gets 6 kilowatt and this is 6.78 kilowatt. The loss which is coming from the open circuit test, that is basically the core loss or the iron loss. And from short circuit test, the loss which is the power which is coming is basically the copper loss. So we have copper loss and core loss. We have to calculate the efficiency at full load, that is x equal to 1, and at a power factor of cos theta is given at 0.75. I think we will all able to solve this also. Try to solve it. Similar to the last problem. Here, Ajana Reddy, you have any doubt? We got the correct answer. Yes, I am unable to mute myself. No, your answer was correct. So you can write over there what is your doubt. But in this problem, one trick is there that this is not the complete core loss, this is not the complete copper loss. So for calculating the copper loss, as I said, that core loss is the fixed loss. But copper loss is variable. So this is operated at an LV side is shorted. So we have to calculate the maximum current, HV current, and after which we have to calculate the copper loss at that current. And after which we can able to put that in the formula. If you put this as the copper loss, then the answer should be different. That will not match with the original answer. Okay. So keep it in mind. First, try to calculate the copper loss, the maximum current, rated HV current. Okay. There is a mistake in the question which I see here. This should be 10 Ampere. So in this problem, we have to, as I said, that some of you have got the wrong answer. First. So the iron loss is coming from the open circuit test, that is 6 kilowatt. And from as it is HV side open, so you can see that from here, from primary side, the rated HV current is KVA rating by the primary side voltage. So if you calculate it, so 500 by 33, 15.515 ampere, right? So this is the rated HV current, but if we see that the short circuit test was performed at 10 ampere. So the copper loss at 10 ampere is 6.78 kilowatt. So the copper loss at rated current HV is 6.78 kilowatt, 0.15 by 10 by 9. So if you calculate it, it will be around what? Now we have to calculate the efficiency. If you put the formula that at full load x equal to 1, so cos theta was given as 0.75, so x kV is 0.75 by if you calculate it, it will be around 94.56%. Suppose you got this answer, 94 is correct. If you got 70 around, not correct because you put the copper loss at 10. Okay. The same question, you have to calculate the percentage efficiency at half load. We have S kVA cos theta at unity power factor. Sorry, X kVA denoted to X at first line plus copper loss plus iron. So here X is 1, kVA is given as 500, cos theta is 1, X is half, sorry, 0.5, so it is also 0.5. Plus, we know the copper loss, calculate it as 15564.73 plus this 6000. So if we calculate it, it will be around 96.19%. Same type of question. Next question, you have to calculate the kVA, output K power actually, at maximum, at which maximum efficiency occurs. So I also tell this formula. So giving the data. This is the data, and we have calculated the iron loss as 6000 watt, copper loss as 15564.73. So now try to solve this. Yeah, fifth question. Yeah, this one. The fifth question, we have to calculate the percentage efficiency at half load. So at half load, x should be 0.5. That is half. And cos theta is given as unity. That is 1. So just put it here. And we already calculated the copper loss and iron loss in previous questions. So just put over there. It's clear.
Yes, sir.
Okay. Now this section is another question, that is you have to calculate the kV output maximum. So I said that uh, in this previous slide, we already discussed it. See, that will be maximum when iron loss, root over of iron loss by copper loss. So just have to put this formula here. Root over of the core loss by the copper loss. Fine. So you know the copper loss. So this can be also written like this x square of PCU equal to PC of PI. I put this one in the question number 1. So here we have to calculate. So what will be the x? That is, this is 6,000 by how much it was? Copper loss was 15564. Put it 15570. If you calculate it, so don't need to calculate. See, we have to calculate the estimate the kV output. So therefore, the maximum efficiency will occur at this load into the rated kV. That is root over of this one into the rated kVA is 500. So if you solve it, that is 310.43 kV. Clear? So if you, at maximum efficiency, what will be the kVA? So kVA should be multiplied by this load factor. So load factor will be equal to the root over of the iron loss and copper loss. Okay. If you have any doubt, you can ask. Is it clear? Fine. So as I said that we have two tests. One is open circuit test, that is basically done to get the um, already said here. See, in the last problem you see that open circuit test is done to calculate the iron loss and short circuit test for copper loss. To see that in this open circuit test, there is a wattmeter here, it's connected, and there is an ammeter and there is a voltmeter. So we have to calculate the core loss. If you see the core, this was the core. So in this test, at parallel, we know that the voltage across the parallel will remain same. In this case, when it is practically done, this voltmeter, the voltage remain fixed, and we have to change the load current, and after which we'll getting the We have to change the load current to the rated current, and we will get the power that is equal to the core loss power. Okay. This is basically the experiment how the open circuit test was done, and see that if we have a wattmeter reading of W0, V1 is voltmeter reading and I0 is the ammeter reading, then the power factor, we know that the power is VI cos theta. Here it is VI naught. So cos theta will be VI1 I naught by W naught. Right. So the working component of this current should be equal to IW V0 W0 by V0. Right? That is equal to VGY. So the iron loss is V1 I naught cos phi, and this is V W0 by V0. So from this we can write that IW is I naught cos phi. It's basically the magnetizing current that is flowing through the core loss. Now the magnetizing component of it can be calculated as IM equal to root over of the no load current, the open circuit current, by the working component of the current. And the equivalent resistance is calculated as R0 is VI1 by I1 is X0. So that is basically taken from here. So this formula we need to know for calculating any question related to open circuit test. This one, and this one is a fundamental formula. We know that suppose in a question you have to calculate the magnetizing component and only the load, no load current is given and the power factor. On that case, you have to calculate IW, and after which you can put it here to calculate the magnetizing current. The resistance is the voltage across the that was calculated by the current, and the reactance will be the voltage by the magnetizing current. Okay. Similarly, the short circuit test was done to calculate the copper loss. So for short circuit test, where that basically determines the copper loss at full load. The first slide, someone was asking like whether this short circuit test was done at full load. Yes, obviously it is done at full load. You can, for calculating the efficiency, you can also run it at other load, but we have to convert it into the rated load. As I solve a problem over there that we have to calculate the maximum rated current and we have to convert it into the rated. Okay. First, from short circuit test, we get the equivalent resistance, impedance, and leakage reactance of the circuit. If you see here that if this is the short circuit test, while doing the short circuit test, uh, the parameters, series parameters are calculated. Suppose this one R1, X1. So in this series circuit, we know that the current from each of the circuit should remain constant. So while performing the short circuit test, the ammeter rating should remain constant. We have to change the voltage into the rated volt. And if you change the voltage into the rated volt, at that point of instant, we got the power we are getting, from which we can able to calculate the copper loss. Okay. So this is basically the full load current by the short circuit current square into WC. As I solved it already in some problem, the previous problem, that if the short circuit test was done at certain load, suppose at I1, but your rated current is IR. So in that case, we have the full load current, that is, this is on the full load current by the short circuit current at I1 square into the copper loss. Okay, that will give the actual copper loss at rating. Right. So here, from here, we have to calculate the secondary side resistance, that is WCIC square. So these are the basic formula. We have to calculate XS. We know that ZS is RS plus K of XS. So we have to calculate XS, that is ZS square minus RS square. So these are the basic formulas and from which we are going to solve some problem. So we have a short circuit and open circuit test performed. So in case of the uh, open circuit test, the voltage, watt, everything is given. The short circuit test was performed at 23 ampere. So we have to calculate the full load current, and after which you can able to solve the copper loss power. Now we have to calculate the equivalent winding resistance, this one. So basically you have to calculate all the parameters. In the four questions, you have to calculate four parameters. The first one is RE at high voltage side. Try to calculate it. Just note down the formula if you require it, and then you can able to solve. Just remember the circuit diagram, then also you can able to solve it by means of KCL KVL. Rajini asks that why wattmeter is connected in series. Can you unmute and ask me what is your query? See, if you're asking about this thing, then how wattmeter is connected here. But you know the basic behind the wattmeter. The wattmeter has two coils basically. One is the pressure or voltage coil. Another one is the current coil. Fine. So we have to calculate the power from the wattmeter, right? That is V into I. So for the pressure coil calculates the power voltage, and this calculates the current. So in this case, you can see that the wattmeter has one terminal in series and another terminal in parallel. So it behaves like a voltmeter and meter combinations over there. That is a different thing you can learn in instrumentation. It has basically two coils. Okay. It's not connected in series. It has two coils, both are connected in different ways. If you have anything more to know, then you can ask me. So this one is a very easy question. I don't know why you are taking so much time. So we have to calculate the REHB, that is the series parameter, and we know that the series parameters should be calculated from the short circuit test. Short circuit test calculated from short circuit test, we will calculate these series parameters. And from open circuit test, we will calculate these parallel components. Why? This is the core. And the short circuit test will determine the I square R losses. So these parameters are calculated from short circuit test. So REH we have to calculate it from the short circuit test. So from short circuit test we have the power as 1300 watt and the voltage is 120 volt. The current is 23 ampere. So what will be the resistance? That is 1300 watt by 23 square. This will give this. So this is basically how much? Around 2.45 ohm. Right. Now, next question we have to calculate XC. Right. XC is
Sir,
also
थोड़ा
a series
sir,
component. Yes,
hello
yes,
sir.
yes.
Sir, why it is taken the short circuit side, sir, in seventh question?
This one, right?
Yes, sir.
Yes, I'm saying it that C. If you see the equivalent diagram of a transformer, then this will represent the pole. Let me use a different color. So this will determine the core of the transformer, right? Right. So from which test we get the core loss? From open circuit test. So definitely from open circuit test, we'll get these parameters, this R0, HV and XM, HV. Now from the short circuit test, from short circuit test, we determine the uh, copper loss. Copper loss basically the I square R X these losses. So the current should flow in series. So we are able to get these parameters, this RE, XE, these parameters we can able to calculate from the current because current is flowing same in series and that is the copper loss and that for which we have to go the short circuit. For that reason, we are calculating the series parameters through short circuit test and we are calculating the parallel or the core components by OC test. So now we have to calculate XM. Okay. So calculate XM, then it will be clear to you. Is it clear?
Yes, sir. Sir, in the seventh question, the answer is 2.545 ohm, sir.
This one was also very, we calculated RE at 2.45, right? Now we have to calculate XC. We know that equal to the total impedance, that is equal to this voltage by the current. Fine. So to calculate it, XC1 square is equal to uh, minus 2.45 square. If we calculate it, it is around 4.6. Yes, what is?
So in last example, we see that we need to calculate the current in
Yeah,
full load, sir. So in short circuit, actually, that we are just taking 23 square. We are
yeah,
not taking a full load current.
yeah. As I said that we have to calculate for short circuit test. From short circuit test, we are able to get the this parameters.
Correct, sir.
So why we are going to take the full load current? Because we are not able to, we are not required to calculate the copper loss. We are asked to calculate the parameter. So the parameter should depend upon the short circuit current and short circuit, yes,
Yes,
voltage.
sir. Got it. So we are just calculating the parameter. That's why we are not taking full load.
Yeah. So if you are asked to calculate the short circuit, suppose you are asked to calculate the copper loss, then it is also 1300. But if you are asked to calculate the actual copper loss at the full load, then you have to calculate through the HV current. Okay.
Yes, sir.
Basically, copper loss is the losses at full load. So that's why we have to go through the full load current. Otherwise, if you're asked to calculate what was the power loss you calculated from the short circuit, that will be 1300, right?
Yes, sir.
Yes,
So,
4.6 you are
anyhow,
saying.
that means if it will be in the ratio, means the losses will increase and the current also increase that way.
Yeah. Because from short circuit test, we are calculating copper loss. Copper loss will
Yes.
definitely depend upon I, and that is a variable loss. Because if your rated load is changed, then your loss is also changed.
Yes, sir. That's why the W divided by I square will be remain same in any rated or this test also.
Because you are given the short circuit test parameters. That's if you're not given the short circuit test parameters, then you have to calculate the LV side
Yes.
parameters. Then you have to go through the open circuit test and all. But as I shown over there, that from short
Yes.
circuit test, we have to calculate LV side.
Yes.
Now we have to calculate the R naught. These are the core loss components, right? So let me copy this figure. Now we have to calculate R naught, and in the next question, you have to calculate X. So try to solve both of these. I'm giving 5 minutes. This is the final. In this question, you have to calculate R naught, and the next question, you have to calculate Xn. Okay. So try to calculate both the questions. I'm giving 5 minutes. Now we have to go through the open circuit test because you have to calculate the core loss components. Okay. Fine. Whether your assignment of this week is similar to this or not.
Yes, sir.
All the questions are same or some similar?
So same, sir.
Same question.
Yes, sir.
In this question, this is a little bit trickier because you are asked to calculate at HV side. Okay. But where it is given, the HV side voltage is not given. Like, let us consider it. How much it is to calculate it? So it is around 4400. Okay. So you have to calculate it in HV side, not in the LV side. Okay. First calculate it in LV side, then convert it. This is the more easier. Okay. See, they have to calculate R now. Since referring to LV side, it will be more easier that we have power, we can go through power, current, go through voltage. It is 330 V square by the power. You can also calculate in this way. I'm calculating two questions into different ways. If you calculate it, it is around. But now we have to refer, you're asked to calculate this, refer to the HV side. So if your HV side voltage is given as 4400, then you calculate it and then multiply it with, right? It will be around, clear. So be cautious when solving the questions that whether it
Sir,
will ask, yes,
sir, 4400 is given or you have taken, sir?
whatever and is given.
Okay, sir. Sir, one more question, sir. R not refer to LV side. It will be means, sir, the 330 by 1600, sir, how it comes, can understand, sir.
See, the power is V square by R, right?
Yes, sir.
So R is V square by power. Or because here the why we are solving through voltage and we are solving the short circuit test through current. Why? Can you tell me? Because I said that in the short circuit test, while performing the short circuit test, the ammeter reading remains fixed or same. Why? Because we are calculating the series parameters. And in series, the current is same. But while for that reason, we consider I square R. This one is the power. But while calculating the open circuit test, that is meant to calculate the core components, right? So the core components, you see that these are parallel. So in parallel, the voltage remains same. In this case, the power can be calculated as V square by Z. Means either it is R or X. Okay. In this case, we can consider voltage, and in short circuit test, we can consider current. So this is the reason behind it. Okay. It's clear.
Yes, sir.
And last question is you have to calculate the magnetizing reactance. Same that's okay. This is the last question. Okay. And here it is not mentioned. Here it is mentioned at HV side. Try to calculate it. I'm giving 2 minutes. The HV side voltage is even same. That is 4400. Okay. 4400. You can give whether you have to given the 4400 or you have to calculate it through the parameter. So let me solve this last question. We have to calculate xn, right? Mm, xm should be equal to the 330 volt by the current flowing through it. Because if you consider this circuit, you see that the voltage across this terminal is fixed and it is calculated as 330 volt. And the current flowing through this from this side is IM and from this side is IW. In explanation, I explained it. So we have to calculate XM. So that will equal to this 330 by IM, right? Basic KCL, KVL we can able to, but IM is not known. So if you have to calculate IM, mm, so this current we have to know that. So this current is 330 by what was the resistance we calculated? 68.06, right? This is 68.06. This current. So IN should be the total no load current, that is I naught square minus IW square. So IW is 330 by 68.06. I naught is 13. So this is 13 square minus 330 by 68.06 square. So this is IA. So put this one over here, and if we calculate, we'll get the XM at LV side. But you are asked to calculate XM at HV side. So this is 330 by IM into 4400 by 330 square, right? If you calculate it, it will be around 475. Is it clear? Any doubt you can ask me. This was the last question. Okay.
Sir,
Yes.
sir, for ninth question, whether we can calculate directly uh, R not in HV side, sir?
Uh, how we will calculate? I will not from HV side.
Sir, after calculating LV side only, we have to calculate HV side, sir. Ninth question, R not value.
Can you ask me another time? I didn't got your point.
Sir, ninth question, after calculating LV only, we have to calculate HP, yes, sir.
Yes.
Sir, can you explain that 4440, sorry, 400 voltage, sir? HV site, it is data given.
Yeah, you asked to calculate it, and the data is given like for 4400. Okay. If it
Okay,
is
sir.
not, if it is not given, then you have to calculate it. For that reason, all the data, sufficient data will be given. Okay.
Okay, sir.
Or anything else? If you don't have any doubt, then I can drop the class now. Okay. Okay, thank you. Good night. Yeah, welcome, Rajni. Yeah, good night. Okay.